Good morning, ladies and gentlemen. A nice, cannot hear you, cannot see you, but, well, I can feel your presence. Very good. So we go on with our course of advanced quantum mechanics, and there is yet another small change, small twist of topic. It evolves. As you remember, a lecture ago, we've been looking at transitions. So all states in quantum mechanics, states of matter or states of irradiation, they've been discrete. And we consider some evolution as transitions between the states. And we could explain many phenomena like spontaneous emission by atoms, lasers, many things. Right. We have missed something, right? We have missed because the only point which we have taken from quantum mechanics is the existence of discrete states. But it's not all. There is yet very important aspect of quantum mechanics, namely, a quantum system can be in arbitrary superposition of the states. And today we elaborate on this topic. We will talking about coherent states, which are some special superpositions of these discrete states. Right, that one could eventually see at the level of unadvanced quantum mechanics, such as elementary quantum mechanics. Right, in the beginning, we will derive these coherent states just looking at very simple systems. But well, once we understood it for a single oscillator, as our logic tells us, we can understand it for a big set of independent oscillators. Therefore, we can have this concept in the context of any field. Fine. So for about a half of the lecture, we will be talking about rather abstract and simple definition of this coherent state and some properties of those. Right. In the second half, we get concrete examples. Most use of coherent states is in theory of radiation, electromagnetic radiation mostly. So we will come back to lasers, and we understand the lasers in terms of coherent states. There will be much talk about coherence and decoherence in this respect. Then we also look at coherent states of particles, where a relevant state of a system is a superposition of different numbers of particles. We will also consider a concrete example of a paradox which arises in the context of quantum information processing. So there is a topic of today. We will make use of this topic in further lectures. Coherent states. Let us see how we can start. Just for a change, I will start the lecture not with a formula or theorem or definition. I will start with some words of wisdom from famous people. Albert Einstein. Just listen to it and try to interpret it. So as you know, every piece of wisdom needs interpretation. Otherwise you don't hear it, and otherwise you cannot use it. Well, they sell beer in pint bottles, doesn't imply that beer exists only in indivisible pinned portions. Good. How would you transfer this wisdom to quantum mechanics? Who can guess? It's better to put it to the chart. I need to mute you. Good. So it's a kind of deep thought. It's not precisely quantum mechanical. It is something about real world. If beer is sold in quanta, it doesn't mean that it exists only in the form of this quanta. Beer can exist beyond cans. No reaction. Okay. Right. Another quote for another Nobel Prize winner. Well, it's relatively recent. Nobel Prize, Professor Glauber. Such states, and we are talking about coherent states, must have indefinite numbers of quanta present. Only in that way they can remain unchanged when one quantum is removed. Yeah, it's something about counting. Let's talk about beer bottles. If you remove a beer bottle from a set, then we have then we have another state, right? But there could be also states when you remove a pint of beer and the state remains unchanged. Would be very good, very nice state, but anyway. Good. What can I say now? It is a kind of poetic way to explain important property of quantum superposition. Yes, perhaps I would better think of some infinite reservoir of beer when you take a kind of a potion. Yeah, the reservoir remains unchanged. A sea of beer. Anyway, let's get to mathematical forms of these things. Right. Let's talk about superposition of photon states. So we specify to a certain field, to electromagnetic field. And let's just have some general statement. An arbitrary state of electromagnetic field does not need to correspond to a fixed number of photons. All right. It is easier to imagine it in the context of photons rather than, for instance, in the context of electrons. Right, so because it is easy to imagine that number of photons is changed by absorption or emission, by interaction with matter. And if we somehow we also have a possibility to excite photons, we can switch light on, and we get the state with plenty of photons, light, so we can exchange it. So let's think of superposition of photon states. Right, so here I sketched an arbitrary superposition, arbitrary wave function of a field. Well, okay, what can I say? There are states in Fock space, which means that there are very long rows of integer numbers. Each integer number gives number of photons in a peculiar state. These states are parameterized by wave vector and polarization. Fine. Then, right, this is time-dependent wave function. And if you recall Hamiltonian of the field, we understand how these coefficients evolve with time. So what comes here is just energy divided by h bar of a certain state. Energy is a summation of individual energies of photons with proper coefficients. Right. So this is a non-stationary state. In distinction from number states, which are stationary. In this case, the coefficient here is 1, and it would not change. Good. Then we the different modes are considered separately, right? Why do we need to sum over the modes in the Hamiltonian? Here, we need to sum up over all k and alpha because there are all these modes present in the field. It's arbitrary state. So the total energy of a state, this state, is a sum of individual photon energies. That's why we sum up here. As to this summation, again, there are these states present, so an arbitrary superposition would necessarily involve all possible states. Oh yeah, we need time and exponent. Very good point. Yeah, there is also time dependent. Fine. Does this answer your question, Sasha? Because this coefficient is nothing but energy of this particular state. No, Sasha, we do not consider a particular K. We consider a state in Fock space. This state is characterized by long number of occupation factors. Number of photons in first level, second level, third level, and so on. C depends on the whole row like this, and not only on a given K. That's why we sum up over here. This is just total energy of the state. Right, curly brackets, it just a shortcut for such a long row. Good, we understand each other. So an arbitrary superposition. Coherent state is a very certain superposition. Let's thus figure out what kind of state is it is. Right. To this end, we do the following. We start with classical oscillator. We start with a classical oscillator. Here it is, capacitance and inductance. And we also include voltage source, external voltage source into the circuit. And we kick the oscillator. Right, in mathematical terms, it means that we apply some external voltage, which depends on time. It's convenient to talk about voltage pulse. Just very short change of voltage. All right, we understand what will happen. Since there's no dissipation, after a pulse of voltage, we excite oscillations. We excite the oscillator to some excited state. We will induce oscillations. Here's the plot. So this is the voltage source. So as we see, we just only gave a short pulse, right? There's some development of current and voltage in the oscillator during the pulse. But when the pulse ends, these values do not go to zero, right? They continue to oscillate, so the oscillator is in some state. The state has energy. We have excited the oscillator. And right, it persists as far as friction is not present. Right, very good. I guess everybody has intuition about this classical problem. Now we will try to understand it quantum mechanically. We know everything about an oscillator, it seems. So we just solve, and this is a bit tedious derivation, but the answer would be sufficiently simple. We will solve for quantum mechanical state of the oscillator after the application of such a pulse. Right. How do we proceed? First of all, let us take something which we have studied when we consider quantization of the fields. And let us use of convenient coordinates, the coordinates in which all oscillators are the same. The coordinates which equally suit any oscillator. And let us see, those are complex coordinates defined like this. As you see, a real part of this is proportional to voltage, and the imaginary part is proportional to current. And the equation for D is like this. As you see, voltage, external voltage, comes as a source term to the simple linear equation. So how we understand the situation in terms of D in the beginning, before the pulse, D was 0. Then we apply pulse, it arose somehow, and then it just remains to circle in time with a frequency, which is the frequency of the oscillator. So that's another way to see oscillations in this oscillator. Very good. So this equation is linear, and it eventually doesn't matter. One doesn't have to specify the time dependence of the source. One can just solve this equation. That's it. Fine. So quantum mechanics. Let us see. Well, as usual in quantum mechanics, there are many ways to look at this problem. Let me adopt here Heisenberg picture. Right, so we take a quantum oscillator. I have a Hamiltonian of quantum oscillator. External voltage comes here into capacitance. I can kind of show it. Right. Then let me rewrite this Hamiltonian in terms of convenience operators that we use, that we made use of, creation annihilation operator of this mode. All right, that's what we have without voltage source. And this is an addition provided by the voltage source. As you see, it's linear in operators. Well, because what we found here, the coefficient is a voltage, and it's a field operator. It's linear function of creation annihilation operators. All right, so we have a modification of our Hamiltonian, time-dependent modification, a piece which is linear in creation annihilation operators. Right, and let us apply Heisenberg picture to this Hamiltonian. Let's make these operators time-dependent. Very well, and we make equations as usual by computing an operator with a Hamiltonian. That's the equation for annihilation operator. As you see, there is extra term, which is a source, and which is actually a number, not an operator. So classical addition to equation, and if one solves this equation, look what one gets. Two terms. First, operator without any external voltage, without a kick. And what the kick gives is a constant term, not an operator, just a number. And this number is expressed in terms of classical solution, in terms of solution of classical equations. So that is summarized here. Creation annihilation operators get a classical addition. Right, so we have solved the operators. We need to, but that's not everything what we want. We want to understand the state. So we need to go back to Schrödinger picture. Next slide tells us how we can do this, how we can derive the state. Okay, it's a trick which will allow us to find the states. To find the state, first of all, let us understand the correspondence. Let us recall the correspondence between Schrödinger equation and the Heisenberg Schrödinger picture and Heisenberg picture. The expectation values must remain the same. So in Heisenberg picture, vacuum in the beginning remains vacuum whatsoever. It is not affected by anything. Operator is affected. In Schrödinger picture, the operator remains the same. Wave function is affected. Very well. So this is a correspondence. This is valid for annihilation operator, but also for an arbitrary function of these operators. Right. Let us take now a concrete form of this function. Let us take, let us substitute what BH is, right? And let us compute the result. How we can compute the result? It looks terrible, but what we can do is the following. The operators BS acting on 0 would give you 0, right? Nothing can be annihilated in the vacuum. B squared also would give the 0. So eventually one can expand this function in powers of this operator and leave only zeros power in the expression, which can be obtained by setting all these operators to 0. Here we are. What we obtain is the following. For any function, the average of this expression is the function itself substituted with dt. But how can it be? It can only be so if a wave function is somehow eigenvalue of operator B, operator B Schrödinger, right? In this case, we can just replace B with D divided by square root of H, and we are here. Good. So we get an eigenvalue equation for this function. Right. I will replace this somehow ugly number with just a letter lambda. So we will have the simple eigenvalue equation. And this equation will permit us to evaluate the state of the oscillator upon kicking. Yep. That's where we are going. Yun's question, do we assume that f is a polynomial? That we might assume. Precise assumption is that f can be expanded in Taylor series around the point D. All right. So let me write it a bit symbolically without coefficients. Expanding in the first term f d, second term b f prime of d plus such Taylor expansion. Fine. Good. Can I explain the last step again? Right. So we look here. This is an equation which determines expectation value of a rather arbitrary operator, arbitrary function of operator B, with respect to very certain wave function, which you want to evaluate. And we see that this relation holds for any function of B, right? Simplest way to look at this relation is to say, well, for this particular wave function, Bs is just replaced by a number. Which number? Oh, this number. Right? Then we are sure that this is valid for any operator. Good. What does it mean? It means for this particular function, action of B is the same as multiplication with a number. So this is this eigenvalue equation. Fine. All right. So we here we understood that this state of kicked oscillator obeys this equation, and that's what we will call coherent state. This is the definition. All right, let us make another step. Let us elaborate and let us compute all these coefficients, all how shall I say, superposition coefficients for this state. First of all, we note that psi cannot be a state with fixed number, right? Because, yeah, it's what Professor Glober said. By when we apply operator B, we remove a photon from the state. But the state remains the same upon multiplication with a number. That's what he meant by his piece of wisdom. Right, we got mathematical expression for this. And we understand that it cannot be done for a fixed number because this necessary change, annihilation of a photon necessary changes this number. Good, so we look for the solution in the form of a superposition, psi of n on our superpositions, superposition coefficients of a state with a given number of photons. All right, so we just plug it in here, and then for then the equation separates in a series of equations for a given n, right? That's what we have. Okay. This is a simple recurrence equation. So we understand that if one knows psi n, one computes n plus 1 just by multiplying with a factor. So we can collect all these factors and express psi of n in terms of psi 0. All right. We just multiply all these factors in a row for all different n's. We got a factorial. Inverse square root of factorial. Very good. Then we need to normalize this function and determine psi naught. Right. Normalization. Fine. So we sum up over n. We implement this formula and we get this expression. Which looks a little bit terrible from first sight, but one could recall that this is eventually Taylor expansion of an exponent, one of the simplest functions we can deal with. So we sum up it over n and we got the exponent. We perform normalization. That's what we got. We got explicit form for a coherent photon state. Okay, this lambda, it's eventually, let me recall that it depends on the voltage source, right? It depends on how do we excite the oscillator. So having different kicks, we have different lambdas in the end, different coherent states. And as expected, it is a superposition, but not an arbitrary superposition. All coefficients in this superposition are eventually pretty certain. Good. Then we will look at the properties of this state. Let us see a bit behind the schedule. Let's look at the properties. It is convenient, you know what, to draw some pictures. But let's make a couple of formulas before we draw pictures. First of all, let us figure out what is the average number of photons in this coherent state. Good, so we just sum up all these psi's. We got squared of lambda. So in other words, this lambda can be expressed in terms of average number of photons times some phase. Lambda is a complex number, so it needs to have a phase. Let us now get to this this convenient coordinates and try to draw some pictures just to compare. This is classical picture. We have seen that. So initially, the oscillator was in ground state and there was a pulse, and it orbits a certain circle. Let us now do the following. Let us plot here the states with a fixed number of photons. Those are circles, right? Those are circles. The radius of the circle is square root of n. Here. So what is the coherent state in this picture? That is blue dot. As you see, it has finite radius. And well, it overlaps, as in this picture, several number states. The number of these number states will become bigger if you go farther from the center. Right, that's one. That's how one can visualize a coherent state. In other words, right, it is somehow here on the circle, but the this of the circle is kind of finite in distinction from classical trajectory. That's how we picture the coherent state. Good. Is it clear to everybody? Any questions about this? It's just much more convenient to talk about formulas. So something which is concentrated around this lambda. You change the phase of coherent state, you replace it here. You change the modulus of lambda, you get it farther from the center or closer to the center. Fine. Let me talk about in more qualitative terms how we get to this picture. More about formulas. Let us first understand that the chance to find n photons in the coherent state are just given the square by the square of how do you call it, by the square of superposition coefficients at given n. Right, it is this expression, and this is well-known Poisson distribution. We have recently seen it in the context of lasers, which rings a bell. But let's postpone it. Right, it's a number of photon states probability to find n photons in coherent state. Average number of this, it's it's an average. As to the spread, it is proportional to average number. This is Poisson distribution. It's a famous distribution of independent samples coming in different areas of physics. Right, you might see the analogy for big N's with a kind of measurement errors. When we measure something, we repeat the measurement, and the relative error, the spread of measurement results, it just obeys the same equation. Very good. So we understand that Poisson distribution is here. Right. So it was a question about previous transparency. But the dot overlaps only a couple of number states. I thought the coherent states had an infinite superposition of number states. To answer this question, it is best to look at this graph, and now I want to put some discrete ends. Is it clear now, Sasha? Right. So, in fact, this dot is somehow approximation. We approximate the Gaussian function which you find here with something like that, which has finite spread. For the sake of a picture. All right. Oh, let us understand that the distribution of this radiation is very different from what we got in previous lecture. Is very different from black body radiation. That's exponential distribution of number of photons, which we have derived in previous lecture, which can be obtained from thermodynamics, in fact. Right. This is a picture. A plot which illustrates the difference. So this is coherent state with a peak, somewhere big number of photons, and this is black body radiation. Just to train you in multiple choice questions, as you remember, there will be multiple choice questions in the exam. If you look at this picture attentively, you would find it perhaps a little bit old-fashioned. So I've taken this picture from a scientific article, and you might want to guess, approximately, of course, how many years ago this article has been published. Right. Let me put it like this, 60. Fine. Your answers, please. Right. I see that A has no. Okay, there are more. There are more questions. There are more answers. A, which is correct answer. So how one could argue? 6 years ago, we would have much more advanced graphics. 120 years ago, well, that is a little bit too early because, well, quantum mechanics has not been formulated by that time. Although people knew something about black body, at least the problem has been formulated, but no quantum mechanics at all. So there is no notion of coherent state. So C doesn't work, and we remain with A. So this picture has been done without computers. It's been just drawn by hand with ink. I still do remember this way of making pictures for scientific articles. Right, good. So I guess you're pretty much prepared for multiple choice questions. But again, it's also general wisdom to avoid extremes. The right answer is always in the middle. Fine. Let us see. Guess it's time for a break. Yes, it is. So let's have like 6 minutes break. We will come back at 9:41. All right, I need to stop the recording. Good. Second half of the lecture. So wave body radiation and coherent state are very different in distribution of photons. Let us mention yet another property of coherent state. It is an optimal state which is obtained from the ground state of oscillator by shifts. And that's again a little bit reminiscence of first coherent state, which has been written down, was not even about a field, was about single operator, and it's been written by Schrödinger himself. And what he did, he wanted to understand which states minimize the uncertainty relation. He just wanted to understand better the uncertainty between momentum and coordinate, typical for the picture. And what he has found that one of the states is a Gaussian function, which is a ground state, a vacuum state of an operator. But very many states which are equivalent to this vacuum state. And those can be achieved by shifting this state in coordinate and momentum. Well, how do we shift it in coordinate? Well, we just replace x with some x minus average x. As to momentum, well, we do the same in Fourier space. And that means we multiply this function with something like, let's see, average p divided by h bar x. And it turns out that these shifted states are coherent states for this particular oscillator. And all right, they also optimize the uncertainty between momentum and coordinate of an oscillator. Right, let us, as a last property of the state, let us understand something which we will need soon. Some qualitative picture. Again, I got back to this picture where the coherent state is drawn as a dot, as a small circle. Right. The radius of the circle in dimensionless coordinates is just 1/2. Now let us determine the angle, the change of phases, spread of phases from which you see this coherent state at large n. It will be like this. Let me also understand the uncertainty of n, the spread. Okay, that we have already computed. We can compute it also from looking at this picture. And this uncertainty is square root. Yeah, and if we multiply these two, we get a number which does not depend on the state. So one can say that this illustrates the uncertainty in a bit different coordinates. There is uncertainty of the phase and uncertainty of number of photons and of direction, tangential direction and radial direction. And right, this is what we can see in this coherent state. Uncertainty between number of photons and the phase. Fine. Let us read it 1/2 come again. Yeah, this is qualitative picture, so it is a bit excess of accuracy, one can say. It comes from the approximation of a Gaussian shape with some number. Best approximation to Gaussian function in terms of a circle. Right. Let me say one simple but important point. We did it everything for a single oscillator, but we can quickly generalize it to all modes which are present in our field for infinitely many modes that we did several times, switching from one mode to many. So in this case, the coherent state of the field will be just direct product of coherent states for each mode labeled by K. And in each mode, there are coefficients, these lambdas, they are different for different case. So generally it is the above one can represent an arbitrary field configuration. Right, so one can find the correspondence between classical solutions of radiation and lambdas of the corresponding coherent state. How one can do this? One can take a formula for field operator of A, and instead of, because of this eigenvalue equation, one can replace all B's and B daggers with lambdas. That's what I did. So if I know the set of lambdas, I can compute classical solution of Maxwell equation. I can do it other way around. If I now take, yeah, what do I have to do here? I need to run Fourier analysis. I need to compute Fourier harmonics of A. And these Fourier harmonics do correspond to lambdas with some coefficients. Right. So each classical solution of Maxwell equations has a coherent state associated with this, with it. Yeah, it's not no wonder we can excite one oscillator, we can excite also plenty of oscillators. So arbitrary excitation of a field will correspond to a coherent state. Fine. Let us now talk about lasers. And now we get to some semantic traps, because coherence in English can be used in many ways, also in um, plenty of physical ways. So we will apply with the word coherent. Let me first say that laser light is highly coherent. What does it mean? It means in optics, optical coherence, that it is monochromatic. In distinction from whatever sun, any black body radiation, we have only single mode in laser. It gives the light at very certain frequency. In this case, this radiation has a phase corresponding to this frequency, optical phase. And it turns out that the phase of a rather practical laser stays almost constant in time. If it were constant, it would have been ideally coherent. For practical lasers, there's some time at which the phase is lost. Phase fluctuates and changes randomly. That's one point, one definition of coherence. And then distribution of photons in the laser. We have computed it in the previous lecture. We did it with a bit different method with transition, but the distribution Poisson, well, almost, because we have to assume that it's a saturated laser. And this is precisely the distribution we got for coherent state. Look, when we got this distribution in last lecture, we were about to draw a wrong conclusion. For us, it would mean that the laser can be in different number states, and there will be fluctuations in the laser when it goes randomly from one random number state to another state. This is not what happens. The laser is almost in the same state. But just to get out of semantical trap, the coherence of the laser does not imply that it is in coherent state. Coherent state just a label for a very certain state. An actual state of the laser is a bit more complex. But nevertheless, coherent states are, as we will see in a small example, coherent states are very useful to describe lasers. They're much better than the description of the laser with a fixed photon number. All right. Anything which I need to explain at this point, at this transparency, at this slide? Good. It looks I could not make it as confusing as I wanted. Anyhow, let us see a concrete example. Let's understand the laser in more detail. Let us first talk about quantum noise in the laser, which in fact is a way to explain quantum mechanics in a bit of classical terms. Let's assume that the laser is coherent state and it's characterized by a parameter lambda. And we apply semi-classical equations, and let's first consider laser without external radiation, when radiation switched off. So then for semi-classical equation, the solution would be zero. Lambda would go to zero to vacuum. Let us try to explain the fact that the state is spread around zero by means of some noise. So we assume it's classical variable subject to noise, to some random noise. And this noise spreads it a bit. So fluctuation of lambda would be 1/2. All right, let us see. First of all, what is this Q, right? It is how laser loses the photons. That's inverse. Q is a quality factor of laser light. So this describes photons going off the laser. Right, so we add corresponding noise. And then we have a picture of Brownian motion around this point. So there is a force which tries to get it to zero, and also Brownian motion around this. And what did I need it for? I want to understand diffusion coefficient corresponding to this Brownian motion. Good, it's diffusion coefficient. It is proportional to quality factor of the laser. Good, this is laser switched off. It's not very interesting. Let's switch it on. Let us understand what will happen. In this case, as we know, the laser would like to be in a state with a great average number of photons. Stimulated emission would draw it. Okay. This number of photons is some equilibrium value when the gain of into stimulated emission is compensated with a loss of into this inverse quality factor. Right. So in terms of coherent states, we understand that equilibrium is achieved not in a point, but for a whole cycle. Right. But this Brownian motion remains in force. So now this Brownian motion would occur along the circle. So coherent state will change lambda randomly in time. And we can estimate how long it will take for this random motion to go over the whole circle and to achieve complete dephasing of laser light, right? That gives us, from this diffusion coefficient, optical coherence time of the laser. As we see, it is very big for a big number of photons in the laser mode, much bigger than the time of escape. Here it is, of a single photon from the laser. Yeah, for a very good laser, this coherence times can achieve seconds. Right. This is there are also different processes like fluctuations of laser parameters which can affect this. So one can say that this contribution to decoherence is just the upper boundary. One cannot have more coherent laser than this estimation. Good. So we talk about the lasers, and finally we got, after several attempts, um, uh, equivalent physical picture of the laser. So the laser is not what we got in the previous lecture, not a fluctuating number, not a fluctuating object which is in a number state at each moment. Better approximation is a coherent state, a superposition. But we also see that this approximation works only on a short times, smaller than this time. But in fact, the laser is described by diffusion of coherent state over a circle, which occurs at some large time scale. Fine. If there are no questions about the lasers, let me go on. So far, we've been talking about radiation, about matter, about photons, something which comes from classical field. We understand that at very top level, there's no distinction between particles and fields. So we would also expect coherent states for particles, and we will give some examples. In fact, we have already discussed such examples without perhaps naming it explicitly. Right. Let us play a little bit with words and let us understand what can be coherent state of particles. For photons, as we have seen, coherent state is the same as classical state, right? A solution of matrix equation, Maxwell equation, sorry, which describes some light, some radiation, can be can be brought into correspondence with a coherent state, making it quantum mechanical. For particles, classical state means fixed number of particles. No, that's natural. Classical particles do not go to any superpositions. Once this number is set, particles can move, collide, but this number is fixed. That's what classical physics would tell us. So, what is the coherent state of particles? And let me now get back to several lectures back. Let me recall that we have considered Bose condensate for bosonic particles, and the superconductor, which also had a condensate of Cooper pairs. And in both cases, there was a broken symmetry involved, and the state of either Bose condensate or superconductor has extra parameter phase. There was a degeneracy with respect to the phase. It can be arbitrary. And this gives us a signal that these states are coherent states, that those are superpositions of the states with different number of particles. So what would be conclusion? Coherent state for particle is in fact a classical state of some quantum fluid, superconductor, or superfluid. And from now on, we will concentrate on simple model where we can illustrate in detail how it is consistent with fixed number of particles. Good, a bit philosophical slide, and I talk a bit. I would appreciate any questions at this point. I don't get how the coherent state for matter is the classical state of quantum fluid. Classical in a sense that it is a characteristic of not an atom or some small system. Classical is that it is a state of a rather bulk material, um, 1 meter long superconducting wire, of a liter of superfluid, liter of superfluid helium. Right, this is about many particles. Quantization of particles, any quantum effects related to this are not important. In this case, it's a classical state. But it is characterized by phase. It has a parameter, macroscopic parameter, which can change. That's why it is a coherent state. Fine. All right, let us go on, and let us first understand two rather opposite limits, and then have a model for something which makes it, which provides a transition between these two oppositions. Right, the question is Landau-Ginzburg theory a case for the coherent states of matter? Yes, in fact, it is. So Landau-Ginzburg theory is, it depends which kind of theory. So Landau-Ginzburg theory is usually about superconductors. superconductor order parameter has a phase, and as such, it is a coherent state. Good, so it looks like positive answer, yes. However, there are also Landau-Ginzburg theories for some other order parameters which have nothing to do with superconductivity, which could, for instance, describe magnetic states, where the phase is actually a magnetization angle. In this case, it's not for coherent states. Fine, right. Let me consider these two oppositions. And we will recall the relation we have recently derived for coherent state. We have recently derived the uncertainty relation for the phase and number of particles. How one can interpret this relation? One can say that, yeah, it's very similar to the relation between momentum and coordinate. So it can be based on the following operator relation between operator of number of particles and operator of the phase. So quantum mechanical representation of this uncertainty relation. What does it mean? It means that usual wisdom of Heisenberg uncertainty applies to this. If phase is well defined, some number of particles is not fixed at all. The fluctuation of number of particles is infinite. And if n is fixed, then fluctuation of phase is infinite. What are the extra particles? Excitations? I'm not sure I'm talking about extra particles, Francesca. I'm talking about the total number of particles in the system. If the system is not in a number state, this number of particles can fluctuate. Number of okay, it just to get an offset extra particles with respect to some equilibrium value. With respect to average number of particles. Let me put like this. Right, not to involve a kind of big number here. Good. So how to realize this situations? That's kind of very simple physically. So we, if we consider bound material which has no boundaries, at least we don't feel these boundaries. The number of particles is infinite. So it has all chances not to be fixed. For a superconductor, for superfluid, phase is fixed in this case. If you do the opposite, if you take an island or droplet of superconductor or superliquid, then we understand that it has to have fixed number of particles, just by definition of an island of isolation. It means that it cannot have a fixed phase. Somehow all configurations with different phases have to have the same probability. All right, that's two extremes. It's easy to comprehend, but it's difficult to understand how one situation transfers to another situation. So we will have, let's make a model for this, and the kind of motivation for this model that we have infinite variations of either number of phase in these two positions, and that might cost energy, right? So the states are not likely to correspond to some exact Hamiltonian. They would cost too much energy. Right, and that model, which I will implement, has rather interesting experimental significance. It is a device which is sometimes used in modern quantum information processing techniques. It is a heart of some qubit realization. It is called a Cooper-Bear box. Let me spend a minute and explain how does this work, how it is implemented in a contact experimental device. Good. So it's a box. It's some place to have Cooper pairs in, and you might be surprised if I just look at this picture. I would say that this is perhaps a box. No, nothing of the kind. The box is here. This elongated piece of superconductor. And all the rest, here, here, and here, is in fact a bulk superconductor, say meters in diameter, and it can be considered as a state with a fixed phase. Right. What is important is a connection between this elongated island and the bulk. This connection is given by this Josephson. Oh, I need different color. By these Josephson junctions. Two Josephson junctions, they are made two in order to tune the number of coupling. Not important. We can just take one Josephson junction to connect this box, this island, to the bulk. Right, and we can wonder about phase and number of particles in this island. Okay, we assume that the phase in the bulk is fixed. We could put it to 0 for convenience. And we will try to understand the peculiarities of the island. It is kind of clear from the model that fluctuations of both quantities, either charge or phase, would give us energy costs, right? If the phases between the island and bulk are different, that costs some energy at this contact. It costs Josephson energy. In fact, a supercurrent would flow to this island trying to change number of electrons. So variance of phase has energy cost associated with the Josephson energy of this junction. As to n, it is just a charge which we put into this island. If one transfers a Cooper pair, you increase the charge by 2e, and that produces field around this island, produce electric field, which also costs energy. So big variance of n also costs energy. So let's have a Hamiltonian which incorporates these energy costs, and we will see what one can do with this. Right. As promised, the Hamiltonian has two terms. First term is associated with Coulomb energy, which is due to extra charge in the island. So here we have operator number of particles, well, Cooper pairs to be precise, in the island, and there is some average value which can be set by gate voltage. Right, we see that this gives a energy cost of large variations of n, which prevents somehow the phases with very definite phase. Right, and as promised previously, there is another term, Josephson energy. It depends on phase, and since a phase is a phase, it kind of periodic. If one changes the phase by 2 pi, it doesn't change. This is a periodic function of the phase. Good. This is quantum Hamiltonian, an operator which is made of two operators, n and phi. As we remember, they are conjugated like momentum and coordinate. The commutator is a constant. Right, which means that we can eventually utilize our intuition about quantum mechanics of a single particle and work with this Hamiltonian in either coordinate or momentum representation. Let us do first, let us make first phase representation. When phase is treated like a coordinate of a single particle, then to n will become something like is associated with momentum of this particle. And this is potential energy. So we have some potential energy and some kinetic energy, which depends on the which is charge and energy, in fact, which is squared of this momentum. Fine. This is showing equation for Cooper pair box in phase representation. Equivalently, one can write it in charge representation. And in this representation, this is diagonal. One can replace n with a number, operate n with a number. As to this term, it does something rather peculiar, but it's kind of not really complex to understand. This cosine is made from two exponents, and each exponent, while working on wave function in chat representation, just shifts the whole wave function by plus or minus 1, depending on plus, minus over here. Right, with this, one can rewrite it in charge representation as follows. Good, there's also boundary condition imposed because the phase is, again, the phase, it's periodic with 2 pi. So the states which differ by 2 pi must be equivalent, which corresponds to the assumption that the charges are discrete. Good, so we have a kind of elaborated model, and in this model we have parameters. Changing these parameters, we can assess both limits of well-defined charge and well-defined phase. So I have 2 slides about this. If we assume that charging energy dominates, then the charge is well-defined, and the levels, quantum states in Cooper per box, are almost pure charge states. The only interesting point might happen, right, so each parabol which I draw here, and I change the gate voltage here, each parabol which I draw here corresponds to a given charge state. Fine. Nothing interesting happens unless these 2 parabols cross. And in this case, we discussed it in the course of quantum transport, but it's rather simple physics. We have degeneracy of 2 levels, which is shifted by small, which is lifted by small Josephson energy. So there are mini gaps formed in the points of crossing, where actual wave functions are superpositions of different charge state. Okay, here we have at least the state with well-defined number of particles. There are still some fluctuations involved. They're small because Josephson energy is small. If the phase is well-defined, let's see what happens. So Josephson energy is much bigger than charging energy. To understand what is going on, let me sketch potential energy in phase space. Potential energy is dominating. And this is cosine function. Then if we look at the low energy states, those are somewhere here, where the potential can be approximated with a parabol. So we have a series of equidistant states. So in fact, the system which we obtained is yet another oscillator. It's yet another oscillator at low energies. That means that as for any oscillator, it is either localized or delocalized in both variables. There is a variation of phase. There is also a variation of n. Yeah, one can say that the square of this uncertainties, product of these uncertainties is 1/2, at least approximately. But if we just look at these uncertainties, we understand that this is state which is localized in phase and very much spread in charge. All right, when one goes to high levels, the potential ends, and the high states are in fact dominated by kinetic energy, so they look more like charge states. Very good. So we have now something which approximates between 2 extremes. ideally fixed phase or ideally fixed charge. Variations would have some energy costs, so they have to be dealt with within this model. Let me finish with something which I just mentioned. This is Cooper-Purr-Box. This is coherent state of matter. But in fact, we see that in certain limits, it is an oscillator. It is an oscillator with a current and voltage as variables. So it's completely equivalent to oscillator made of capacitance and inductance. So in fact, coherent states of matter in this particular example are just nothing but coherent states of radiation. And at this point, both states come nicely together. Which again, an illustration of the fact that at top level, there is no difference between particles and fields. There is a single advanced quantum mechanics which unites everything. Good. Let me, at this point, at this high pitch, finish this lecture. I will stop